Hello everyone. Today we're going to look at simplifying radicals and just some of the basics. I'm pretty sure you've done simplifying radicals in the past, so therefore this first part should be a review for you. So first off, a couple of terms you need to know. The radical sign, we've been talking about a lot about radicals last chapter at the end. Well, the radical sign is just that square root symbol. Square root, if you recall, that means a number times itself 2 times to equal the radicand. So radicand's a new word. Radicand is the number that's underneath the radical. And then index is that root. So root and index kind of go together. For a square root, remember there's always a 2 here. And then a radicand is what's underneath the radical. Perfect squares. We're going to be using perfect squares a lot for simplifying radicals. Remember, your perfect squares are numbers you can take square roots of that give you perfect squares. So the way you can create a list of perfect squares is just take every number and square it. So 0 squared is 0, 1 squared is 1. Those are really your first two perfect squares. But when we simplify radicals, 0 and 1 won't really be used. That's why I put a box around them. Then you can just square every other number. 2 squared is 4, 3 squared is 9. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, and 12 squared is 144. And again, we can keep that list going on really forever, just taking the next number and squaring it. But you are going to want to see that list of numbers in front of you, that perfect square list, when we simplify radicals. So why do we simplify radicals? Sometimes you want an exact answer when working with square roots instead of using a calculator to find approximations, which are the decimal values. So the way we keep answers exact is you need to leave square roots in the radical form. So here are your steps for simplifying radicals. You look for perfect squares as factors of the radicand. So that number underneath the radical, you try to see which of these numbers in here divides evenly into that radicand. Preferably, you always want to look for the largest perfect square, so I always start on the right side of my list, and then I'm really just saying, does 144 divide into it? The radicand. Does 121 divide into the radicand? I go all the way down to 4. Once you find one, you can stop. So once you find that perfect square factor, you're going to rewrite the number under the radical as 2 factors. Step 3, then you can write the 2 factors as 2 separate radicals. Step 4, take the square root of the perfect square. And last but not least, you multiply the square root of the perfect square by the reduced radical. When we say the word simple radical form, again, that's kind of another vocab word. It's the product of a number and the remaining radical when there are no more perfect squares factor underneath the radical sign. So in regards to product, that means multiplication. And then we're looking for a number in front possibly, and then no perfect square factor underneath that radical or within the radicand. So examples of a perfect square or simple radical form, simple radical form is 2 times the square root of 3. It's a product because it's multiplication. There's a number in front, and there are no perfect squares, none of those numbers listed above, that divide evenly into 3. So 2 times the square root of 3 is simple radical form. A non-example of simple radical form would be 3 times the square root of 8. Reason 3 times the square root of 8 is not in simple radical form is because 8 can have a perfect square factor within it. 4, if we look above at our perfect square factors, 4 divides evenly into 8. So what we'd want to do is we'd want to rewrite this as 3 times the square root of 4 times the square root of 2, because the square root of 4 times the square root of 2 is square root of 8. And then take the square root of that perfect square factor. Square root of 4 is 2. So I have 3 times 2, and I still have my square root of 2. And so ultimately, that would be equal to 6 times the square root of 2, because 3 times 2 is 6. So 6 root 2 is simple radical form, 3 root 8 is not. All right, so here are some other examples. And again, these examples are really following those steps above. So if example 1 is the square root of 18. So we're looking for what perfect square divides evenly in 18, preferably starting on the right. Well, there's not a whole lot of perfect squares that are even larger than 18, so we can really just start at 9, and in this case 9 does divide into 18. So I'd rewrite this as 9 times 2, because 9 times 2 is 18, all underneath one radical. And if the radicals those two numbers are separate by multiplication underneath one radical, I can then write that as two separate radicals. 9 times the square root of 2. Square root of 9 times the square root of 2. And then you take the square root of the perfect square factor, like it says in the notes. So square root of 9 is 3. Notice there's no more radical around it. It's just a 3. 3 times the square root of 2. And that is simple radical form. Just remember, if you do have a perfect square underneath the radical, you take that perfect square. So for number 2, 9 is a perfect square. And the square root of 9 is saying what times itself is 2 times is 9? Well, that's 3. So the answer here is just 3. When you are taking square roots, you should no longer have any radicals around those numbers. It is just 3. All right, next example is the square root of 80. And again, the whole goal here is to see what's the largest perfect square that divides into 80. So as you start your way down, you can always kind of take that number and divide it in half. So half of 80 is 40. The next closest square to 40 is 36. So 36 doesn't go into 80. 25 does not divide into 80. 16 does divide into 80, however. And 16 divides into 80 5 times. So 16 times 5 is 80, so I can rewrite that as the square root of 16 times the square root of 5. Notice I kind of skipped this middle step as I did number 1. Once you know, if you feel comfortable enough, you can skip this step where you're writing it underneath one radical and just go right to two radicals that are being multiplied together. The square root of 16 is 4, and I have 4 times the square root of 5. And that is simple radical form as we discussed. So let's say you missed that 16 was a factor of 80, and you said, well, 4 goes into 80. So yeah, you could go ahead and say, well, 4 times 20 is 80, so square root of 4 times the square root of 20 would be the same thing. And it just so happens 4 is your perfect square root of 4 is 2, you end up with 2 root 20. However, that's not what we said was the answer, because this is not simple radical form right now. Because there is another perfect square that divides evenly into 20, and that is 4. So then you would have to keep going. So you have to say, all right, well, 4 times 5 is 20, so I'd write that as root 4 times root 5. Take the square root of 4, which is 2, and then I'd end up with 2 times 2 root 5, which again is 4 root 5. Same answer, but notice how I said before, you always want your largest perfect square factor, because otherwise it's going to take more steps. Where 4 was a factor, but it's not the largest, therefore it took us really double the steps. So always look for your largest perfect square that goes in, divides evenly into it. If we have a number in front, like a 5, remember that's 5 times the square root of 9. So 9 happens to be a perfect square, so I just have 5 times 3 here. 5 times 3 is 15. Now here, for number 5, we have 3 times the square root of 98. In this case, 98 is not a perfect square, so we want to simplify a radical like we normally do. What perfect square divides evenly into 98? In this case, it is 49. So I'd write this now as 3 times the square root of 49 times the square root of 2. And the square root of 49 we know is 7, so we would take the square root of 49 and get 7. So 3 times 7 times the square root of 2. And then I do multiply those two numbers in front. 3 times 7 is 21. And we get 21 times the square root of 2 as our final answer for that. Then number 6, we have root 44 over root 25. So the way we do this problem is we write this as two separate radicals. When it is dividing like that, I can take the square root of the top and the square root of the bottom. The square root of 4 is 2, and the square root of 25 is 5. So here we would end up with 2/5 as our answer. All right, take a second and try those three on your own at the top of the page. Pause the video and see what you can do. All right, try checking your answers for these three. You should have gotten 2√2, 12√6, and 3/7. If you have questions on those, let me know in class tomorrow and we can go over those. We can also do other operations with radicals. First off, we're going to look at multiplying radicals, and this is a fairly easy operation we can do. When you multiply radicals, you multiply the coefficients and you multiply the radicands. Put the multiplication of the radicals underneath one radical. So, for example, if I have 5√6 times 2√2, again, this is all multiplication. So really what I got to think about is rewriting this because it's all separate by multiplication. So I can think of it as putting the 5 times the 2 first, times the square root of 6, times the square root of 2. And then I would do, again, multiply my coefficients. 5 times 2 is 10. And multiply the radicands and put them underneath one radical. So I get 10 times the square root of 12. So this is really the reverse process of what we did on the other page, the first page. In the first page, we had one radical. We made it two separate radicals separated by multiplication. We can reverse that process. If we have two radicals separated by multiplication, we can make it one radical. Now, we're still not done with this problem because, again, we have a perfect square that divides evenly into 12. In this case, 4. So 4 times 3 is 12. So I'd rewrite it as 10 in front, root 4 times square root of 3. Take the square root of 4, which is 2. And I end up with 10 times the square root of 2. Multiply that 10 and 2 together. And we end up with 20√3 as our final answer. For number 2, I have 3√5 times 4√7. So again, the quick way to do that is multiply your coefficients. 3 times 4 is 12. And 5 times 7 is 35. So I'd have 5 times the square root of 35, 12 times the square root of 35. Remember, you multiply the radicands and put them underneath one radical. In this case, there's no perfect square that divides evenly into 35, so you would just stop at 12√35. Okay, we're going to go down to try this on your own number 3 because it's a little more difficult. So if you look at number 3, you want to think of this as 4 separate radicals, so square root of 48, square root of x to the 20th, square root of y to the 10th, and square root of z to the 15th. So you simplify the square root of 48 the way we have been. For the square root of x to the 20th, you're thinking what times itself is x to the 20th? Well, 20 is not a perfect square, but that's not what you're thinking. You're thinking x to the 10th times x to the 10th is x to the 20th, because if you remember those law of exponents, you add the exponents. So here we'd really be ending up with x to the 10th. So the square root of x to the 20th is x to the 10th, because x to the 10th times x to the 10th is x to the 20th. And again, I'm simplifying the square root of 48 as square root of 16 times the square root of 3. Here I'm taking what times itself is y to the 10th, so that's y to the 5th. And ultimately, the shortcut here is you can just take those exponents and divide by 2. Well, now when we get to an odd exponent, what we're going to do is we're going to rewrite that as square root of x to the square root of z to the 14th, which is your next lowest even number, times square root of z to the first. And once we do that, then we can take the square root of z to the 14th, which is z to the 7th. I also took square root of 16 in this step, which is 4. And then I just clean up a little bit at the end, and I do 4 times x to the 20th times y to the 5th times z to the 7th. And then the 3 and the z are both underneath a radical, so I take the square root of both of them. All right, try those other 3 on your own, 1, 2, and the 3 up here. Take a second, try those, and then we'll go from there. All right, so you should have gotten for number 1, 18√2. You did have to simplify the radical after you multiplied it. Should have just gotten 12 for number 2, and then 6x to the 7th, y to the 13th, z to the 25th for number 3. When you divide radicals, you're really just dividing each individual part, so the numbers and then the radicals. So for the number 1, I'm going to rewrite that as 9/3. 9/3 is 3. I'm going to rewrite this under one big radical, so it'll be 125 over 5. Square root of 25 is 5, and 3 times 5 is 15. And you can see how I did something very similar for number 2 as well.